Okay, so welcome to the 33rd video in the discrete structure series, and we're going to resume yesterday's discussion from recursive definitions and structural induction. So yesterday we looked into the basics of a recursive definition, and inside of recursive definitions we looked at the recursive definitions for functions as well as a couple of recursively defined sets. So today we'll be looking at the third category of recursive definitions, and these are called recursively defined structures. And this is really a broad category. A recursively defined set as well as a recursively defined function can be called a recursively defined structure. So these are really any mathematical structures which can be defined recursively. And as part of our course and today's discussion, we'll be looking at the following recursive structures. We'll be looking into a structure called the well-formed formula. We'll recursively define a well-formed formula in propositional logic as well as using operator and operands. And the next structure that we're going to look at is going to be trees. And inside of trees, we'll be looking at rooted trees, full binary trees, and the extended binary tree. So this is going to be the scope of today's video. And before getting started with the first topic of well-formed formulas, a very quick recap. So yesterday we established that a recursive definition has two main components. The first component was called base or seed cases. And for a recursively defined function, the base cases included the values of the function at some initial points. For recursively defined sets, the base cases provided an initial few members or the seed members. And once the base case was established, the second step was to provide a recursive definition. And the recursive definition would essentially be a process of breaking down the problem into smaller problems of similar nature. So in case of a function, the value of a function at some larger value was defined in terms of the values of the function at smaller values. For example, in the Fibonacci sequence, any term would be the sum of previous two terms. And in case of recursively defined sets, our recursive definition would allow us to build new members from existing members. And this pattern of definition is going to stay consistent across today's lecture when we introduce these kind of structures. For example, in case of a well-formed formula, we'll start our base case by providing the simplest well-formed formulas. And then we'll provide a rule to derive new and complex formulas based on existing formulas. And that will be our recursive definition. In case of trees, our base case will include the simplest forms of trees. And the recursive step will allow us to generate new trees based on the existing trees. So I really wanted to bring you on the same page about what it is we are doing today. And assuming that we are caught up with the ideas from our last lecture, let's get on to well-formed formulas. So well-formed formula is a formula that has no errors and can be resolved in an unambiguous way. And to build a basic intuition, let's have a look at a few examples. So this is just a mathematical formula for a product of 7 and 5. And this is a well-formed formula because I know what a product is, and 7 times 5 can be unambiguously resolved into 35. But what happens if I give something like this, 7 times 5 plus? Now this obviously is not a well-formed formula because the addition operation requires at least two operators. And our goal today will be able to come up with a recursive definition for a well-formed formula. The definition that we give should be able to generate a family of well-formed formulas, and every possible well-formed formula should be covered by our definition. And there should be no way to use our definition and reach a formula that is not well-formed. But we should understand that formulas are written in a lot of different disciplines. This one here is an arithmetic formula. We could write a formula using sets and set operations. We could write a formula about a Boolean logic expression. So in order to study this properly, we'll narrow down the domain a little bit. We'll be first looking into well-formed formulas in propositional logic. And when we are talking about propositional logic, our possible operators can be complement, the conjunction, disjunction, implication, and biconditional. We could also consider the XOR or other operators if we need to, but the idea of the recursive definition is going to apply similarly regardless of the number of operators. So these are my operators, and the possible values of my operands could either be a true, or it could be a false, or it could be any proposition S. And when we mention here that S is any proposition, we are just being general. So later on our recursive step, we could assume any proposition P, Q, R, S, or anything like that. So coming back to our objective, we want to provide a recursive definition that can produce all well-formed formulas using these operators and these operands. For example, P and Q is a well-formed formula, and we should be able to produce this. We should be able to say something like A XOR B implies C. We should be able to use the complement operator, for example, like so. But it should be impossible to get something like AND PQ because this is not a well-formed formula. Okay, so we'll get started with our base case. So our base case will involve the most basic formulas. And the most basic formulas will either be a single true a single f, or a single proposition. So we'll describe our base case by asserting that these formulas are already well formed. The formulas true, false, and as, where as is any proposition, just like we did here. And now we come to our recursive definition. And in our recursive definition, we'll provide all valid ways of combining these propositions with these operators. So we'll say the following. So if we have already well-formed formulas E and F, the following formulas are also well-formed. The reason I'm using two variables E and F is because I need at least two variables in order to do a conjunction or a disjunction. So when I start listing the well-formed formulas that can be formed using E and F, the first one is not E. I do not need to mention not F because a path from E to not E already exists for the complement. The next thing I'll describe is a conjunction. I'll write E and F. And it's essentially going to be the same for all the remaining operators. So we're going to write E or F. E implies F. E is biconditionally implying F. And finally E XOR F. And this completes our recursive definition. The important thing to be able to see here is that this definition allows me to generate any valid formula. For example, let me show you how we can get into this formula. So the base case tells us any proposition by itself is a well-formed formula. So I can assume that A, B, and C are well-formed. And I just see what I need here, A XOR B. This rule tells me that A XOR B is well-formed, given A and B are well-formed. Therefore, I can write that A XOR B is a well-formed formula. And this rule says if I have a well-formed formula, complementing it is also a well-formed formula. So I can use that rule to get not A XOR B, and I can use the rule of implication from this expression and C to get implies C. So these rules will be able to generate exactly all the possible well-formed formulas, and not a single formula that is not well-formed can be reached by this definition. There is no way to get AND PQ using any of these rules. And one little thing that is really obvious to miss, and I have missed it here too, we need to parenthesize all of these. Because if we don't parenthesize this, the associativity will not be well defined. Because without parentheses, we are able to generate something like A and B or C, which technically speaking is not a well-formed formula. Because if you mean A and B or C, it means something, and A and B or C means something else. So by using the parentheses, I can make sure that the associativity is never lost. So this is important. And so let's carry this idea of a well-formed formula from propositional logic, and we'll look into one more example of a well-formed formula. So let's look into an example that involves arithmetic operator and operands. And we already know the core concepts. We can go through this quickly. There will be a basis step and then a recursive step. Now what exact operator and operands we choose is up to us. But let us make sure we can at least capture the basic operators. Let's say addition, subtraction, multiplication and division. And let's represent exponentiation in this way. Okay. So instead of writing 2 raised to the power 3, I want to write 2 to the power 3. And for operands, let's consider all numbers and variables like x, y, and z, so on. So you want to probably mention that in language if you want to do this formally. Let's consider the following set of operators and let the operands be one of the following possibilities. Now in the base step, we want to identify the most simplest forms of well-formed formulas. And in our case, the most simplest forms are going to be a single number or a single variable. So on the basis step, we'll just say x is well-formed if it is a number or a variable. Okay, and for my recursive step, how many elements do I need to pick? The least elements that I need is still 2 because addition requires at least 2 operands, and so does all of these others. So we'll just assume let P and Q be well-formed formulas. Then the following formulas are also well-formed. And let's capture the concept of each of these operands. Plus requires 2 things. So I'll say P plus Q is a well-formed formula. Another I want is a P minus Q. I'll say P times Q is well-formed. The division comes in P divided by Q, and then the exponentiation P raised to the power of Q. And do we need parentheses here? We absolutely do, because associativity needs to be preserved. It is one thing to divide and subtract, and it's completely different to subtract and divide later. And similar to the last problem, we'll be able to see that any arithmetic well-formed formula can be derived using these steps. Alright, with that we'll move on to the next topic, recursively defined trees. So there is an entire chapter on graphs and trees later, so we'll be coming into these topics in a lot of detail. And therefore at this point, we'll only worry about providing a recursive definition for 3 types of trees. But if you are completely unaware of what a tree is, it's just a hierarchical data structure. So a tree has a root. It may not have, an extended binary tree doesn't have a root, but for the basic concept, let's assume that it has a root and then it has children. There could be any number of children, and this is just generally speaking. We'll start imposing some restrictions later, but this is what a tree looks like. And a few terminologies, these things are called nodes or vertices of the tree, and you could clearly see that these are hierarchical in nature. I could say that this node is a child of this node over here, So this is the parent and this is the child. And you should also see that this is the topmost node, kind of like the grandfather of all nodes. So this is called the root node. The nodes at the end are called leaf nodes. And a tree has a lot of application. The most common application is as a data structure. Many processes and data in real world are inherently hierarchical in nature. So a tree data structure works best in order to record those kind of data. And one more basic terminology, this is called an edge. So an edge is a connection link between one vertex and another. And all of these nodes and these edges can represent anything depending on what the tree is built to study in the real world. But again, for our purposes, we'll look into how we can define structures like this precisely. So the first definition that we'll look is called a rooted tree. So this is a tree that has no restrictions, but one root must exist. There must be a root element. The root element can have any number of children, and any child can have any number of children to follow up. So a rooted tree is essentially a family of all possible trees, but that has to have at least one root. And like I mentioned earlier, the way we are going to define this recursively is by first defining the simplest form of a tree and then defining a rule to build bigger trees based on that tree. So we'll write the basis step first. In the basis step, we'll mention that a single vertex R is a rooted tree. So we are saying that if we have only one node, the root, it is also a valid tree. Now we'll provide our recursive step. And let's understand this first. You know that this is already a tree. A point is already a tree. And we will say that you could collect any number of trees. Okay. And they should be disjoint. So this is not connected to this. This is not connected to this. So I've taken 3 of these trees. And we'll say if you take any number of trees and then you create a new node, and then if you connect that new node to the root of those previous trees, the structure that you get is a new tree and it is a valid tree. And let me repeat that again. You could take any number of existing trees. Okay. So this could have children on their own. That doesn't matter. And you should connect the new root element to the root of the previously existing trees. And if you do that, the resulting structure is also a rooted tree. So let's mention that definition. If we have disjoint rooted trees T1 to Tn with roots on R1 to R1 respectively, the structure formed by connecting a new root R with all of the existing roots R1 to Rn is also a rooted tree. So let us see an example of this definition. I'll draw a sample tree here. So let us say I need to generate a tree that looks like this. I'll just draw something random. I did not want to draw a binary tree, so maybe one more node here. So let me start applying this definition. I know that a single node is a tree. So let me take 5 of them. 1, 2, 3, 4, 5. And I have a recursive step. I could take any root and connect it to a previous tree and that would be a valid tree. So let me do that with these first 2 nodes. I'll consider a new root, connect it here. And I'm allowed to do because of this definition. This definition tells that this is also a valid tree. And again, the order and position of these points is not significant at all. So I'll be combining these 2 nodes into a new tree. And here's the argument for the second round. We know that this is a tree, right? Because it is coming from our definition. And we know that this single point is also a tree. And now if I follow the same definition, if I consider a root and connect it with the root of these 2 trees, this is a valid rooted tree. And you can see that my task will be completed if I take one new root element and apply the same logic. This is a tree, this is a tree, and this single point is also a tree. Therefore, if I consider this new point and connect with the roots of the existing trees, I get a new tree. Okay, and this tree is equivalent to this one. Alright, so 2 more types of trees and then our lecture will be done for today. The second one we'll see is a full binary tree. So we already know what a rooted tree is. This is just a rooted tree with some restrictions. Because this tree is binary, every parent can only have 2 children. And because this tree is full, each parent must have the 2 children that it can have. So there cannot be a parent that has only one child because that would make this kind of not full. Okay, so full in the sense that each parent will have exactly 2 children, or it would just be a leaf node with no children of its own. So if you want to define this formally, a full binary tree is a binary tree in which the number of children for every node is either 0 or 2. Okay. And so what would be different in the recursive definition? See, we took any number of trees previously, and then we took a new root and then we connected it to the roots of all the previous trees, and that would cause us to have more than one child. But in this case, in our recursive definition, we are only going to take 2 trees. And we're going to take our root element and connect the root element with both trees. And if we proceed recursively in this fashion, we'll make sure that every element has exactly 2 children. And needless to say, it could be a child node with no children. So what is the basis step? We'll again say the same thing. A single node R is a full binary tree. Let us call it vertex for consistency. And what will be our recursive step? It will be exactly like our last definition, but we'll not take n trees, but just 2 trees. So if T1 and T2 are already binary trees with their roots at R1 and R2, then a new tree formed by connecting a new root element to both root elements R1 and R2 also produces a full binary tree. So we have already written this in language in our previous problem, so I'm not doing this here, but it should be quite simple. And the last recursive definition that we're going to look at is going to be extended binary trees. Now, as the name suggests, these are also binary trees with some flexibilities added. The previous two trees that we looked at needed to have a root element. Here we're going to change that. We're going to say that the empty set is also a binary tree. And then one single node is obviously a binary tree. No doubts here. And when it comes to the children of any node, there is flexibility in there as well. So a node could have just one child or it could have two children. Remember, in the full tree, we wanted it to be either 0 or 2. Here we are saying it could be 0, 1 or 2. Obviously, because of the name binary, it still cannot have 3 children or more, but it is not restricted to either 0 or 2. So we want to create a definition that also allows an empty set for a binary tree and covers all binary trees. For example, this would be a valid tree, and you should be able to observe that this is not a full tree. The definition that we looked at earlier cannot generate this tree, because in order to merge this node, you need two valid trees, right? There is no tree on the left. Okay, so let's write a new definition that supports these kind of trees. I'll write my basis step, and this time on the basis step, I want to start with the simplest term. I want to say that phi is an extended binary tree. And next, let's give our recursive step. And can you see the primary difference between our previous problem and this one? Here we need to achieve a situation where a parent can have only one child. Okay, so we'll say that it can be joined into phi because phi is already an element. And because phi is an element, we have that flexibility. We can still say that every parent needs to have two children chosen from the existing set of trees. But that definition is flexible because I can simply choose one child to be phi. Okay, and that will allow me to represent a tree with just one child. So let us make it even more clear with this definition. We again need to assume only two subtrees because this is a binary tree. So we'll say if T1 and T2 are disjoint binary trees, then the new structure found by connecting a new root R to each of the roots R1 and R2 of trees T1 and T2 whenever these trees are non-empty. So this is saying that I could take any two trees T1 and T2 and one of them could also be phi. Then I can consider a new parent root and connect it with the root of the trees I considered. But the connection should happen only when the trees are not empty. So let us also see this with an example. We'll try to reproduce this tree, and I think the initial two steps are the most important to understand. So it should be easy to see that in this case I cannot start with a root node because that is not in my basis step. My basis step only allows phi. But I can use this recursive definition to derive new trees. For example, this says that if T1 and T2 are disjoint extended binary trees, but to begin with I only have phi, so I'll assume phi to be both T1 and T2. Then it says that a new structure found by considering a new root R. So let that be this root R to each of the roots R1 and R2 of T1 and T2 when these trees are not empty. So in this case, both trees are empty, so I don't need to do any connection. So this one node not connected to anything. What will that produce? It will just be one node. So the first step is the basis step, which produces the empty set, and the second step produces one node. And now I can take two of these nodes because this node is a binary tree that I've just established. And if I take two of these and take one more root element, I can form this structure. Now what do I do to form this node? You can see that its left child is empty. I do not want anything on the left of it. And on the right, I just want this tree. So I'll just consider phi and I'll just consider a new root. And on the left side, it doesn't have to be connected because I only need to connect if the trees are non-empty. But on the right side, I do have to connect because it's a root. So a really basic concept, the only thing to understand is that we use phi if we want to skip a certain node. And once we are at this point, we just want to consider this node like so and just apply the recursive definition one more time. And once we do that, this is equivalent to the tree that we're looking for. So this definition is enough to produce this tree. Alright, so that is the discussion for this video. And all of these structures that we looked into in today's video are going to be extremely relevant in tomorrow's discussion. So tomorrow we'll be looking at structural induction, which basically involves proving that all of these structures are consistent and valid. So understanding of the structure obviously comes as a prerequisite in order to make those proofs. And with that said, I'll see you guys in the next one with structural induction. Until then, have a good day and bye.